As what we can see, statically indeterminate problems are very often difficult to solve. Just now we solved a statically indeterminate problem by using methods of superposition and geometry. For this problem, we will mainly adopt geometry to solve the problems. First, let's get familiar with this problem. A rigid bar of weight 800 newtons hangs from 3 equally spaced vertical wires. 2 of them is made of steel, while 1 of them is made by aluminum. The wires also support a load P acting on the bar. The diameter of the steel wires is 2 mm and the diameter of the aluminum wire is 4 mm. It is given that the Young's modulus of steel is 210 gigapascal, while the Young's modulus of aluminum is 70 gigapascal. Firstly, we consider if the load is located in the middle, what load can be supported if the allowable stress in the steel wires is 220 million-pascals and that of the aluminum wire is 80 million-pascals. Besides, what is the allowable load if it is positioned at x equals to a divided by 2, which means what if the load is shifted leftward? Besides, we have to repeat this problem by switching 2 wires such that those 3 wires are not symmetrically distributed. Now let's consider each problem one by one. Problem A asks us to find the allowable load P of the system. Before we start, we try to analyze the free body diagram of this bar. For this rigid bar, there were 5 forces acting on it, the weight, and 3 forces by the 3 wires. Apart from that, we still have an external load P acting on the system. Firstly, we consider statics because the equations of statics are very easy to find, so we do it first. For force equilibrium, it is significant that the force of the 3 wires equals to the weight plus the external load. While talking about the moment equilibrium, it is also significant. The moment about its center of mass is given by APS2 minus APS1. So we take counterclockwise as positive. This is A. APS2 will generate a positive torque, while APS1 is the negative torque. Well, the sign convention is not that important at this stage. We just want to obtain equations for the relationships between different forces in the wires. So we know this after we considering the moment. Next, we consider the allowable elongation of steel and aluminum wires by taking the change of length formula into account. All the wires will be stretched, but we don't want any of them goes beyond the allowable deformation. So we try to find the allowable deformation of each wire. The allowable elongation of the steel wire is given by PL divided by EA, but you know P is not given in this problem, but we know P divided by A equals to stress. So it will be stress times L divided by Young's modulus, which is 220 million-pascal times 150 millimeters divided by 210 gigapascal. The answer is 0.157 millimeters. Similarly, for aluminum wire, we try to compute its allowable elongation. The result is 0.171 millimeters. However, as what I just mentioned, I don't want any of them go beyond the allowable elongation. Therefore, we will take the elongation of the 3 wires to be the smaller value, which is 0.157 millimeters. Let's find the maximum allowable load for each wire according to those 2 information we found in previous slide. As we know, the allowable change of length, the allowable deformation is set to be 0.157 millimeters. It is the allowable deformation of steel. Therefore, we also apply this deformation to that of aluminum and the steel. For allowable load of aluminum, P, we change the subject of the deformation formula, delta equals to PL divided by EA. That means P equals to EA delta divided by L. The allowable load for aluminum equals to 70 gigapascal times its cross-sectional area. Recall that those wires are circular in cross-section, times its allowable deformation divided by its original length. Then the allowable load will become 921 newtons. Similarly, we substitute the values into this formula. We know that the Young's modulus of steel is 210 gigapascals, and the cross-sectional area for the steel wires is that small. Finally, we do a lot of calculations to get the allowable load in the steel wire is 691 newtons. After recomputing all those things, we can apply the statics equilibrium. That is, we put all the PA, PS, all the stuff into the formula. Then we can get allowable load on the system, which is 1504 newtons. For the next problem, it changed a little bit. Now P is not located in the middle. It is shifted to the left hand side. For this problem, it will become rather complicated, but significantly, the inclination of this bar would be like this. Consider the statics of the overall system first. From force equilibrium, we have this equation, while for moment equilibrium, we have this. It should be taught in statics and dynamics, so I don't repeat this part. By simplifying those two equations in this system, we can get this system of equations. Besides, there is one thing that we can verify, is that from the first equation, we know that the load in the S1, the first steel wire, is greater than the load in the second steel wire by 1/2 of the applied load. And this inclination verifies this result, that the elongation of the first steel wire will be longer than that of the second steel wire. Now we should consider one thing about the geometry of the system. We know that the bar is rigid. That means this side is always a straight line. We know that the loading for S1 is larger than that of S2. Therefore, we know that the inclination of this bar is like this. It is the original length of the bar, while the elongation of each wire will then be linearly distributed. From this geometry, we can write that the change of length of aluminum wire is the average of change of length of the first steel wire and the second steel wire, which is written as delta A equals to delta S1 plus delta S2 divided by 2. As what we found in part A, the allowable elongation of the steel wire is 0.157 millimeters. In this entire system, the maximum elongation occurs in the first steel wire. Therefore, the load for the first steel wire is selected to be 691 newtons, as found in part A. Now we simplify the system of equation a little bit to get another equation. Notice that now PS1 is known, weight is known. Next, we have known that PS1 equals to 691 newtons. Now we consider the equation of geometry. Then we apply the change of length formula and substitute into each term each change of length of this equation obtained from geometry. And then we simplify the system to be like this. Substituting all our data into this equation, we can have a relationship saying that the load of the aluminum wire is 2/3 of PS1 plus PS2, the load of the two steel wires. Then we do another substitution to get this result. From geometry, we just get this equation. From statics, we have this equation. Combining those two equations will give you the answer of the allowable load, which is 820 newtons. Now we change our problem a little bit, such that the line A and S are switched. Now the two steel wires are located next to each other. while A is located on right hand side. The system loading is shown like this. We want to find the allowable load P under this system if those two wires are switched. While it is rather similar, by using statics, we obtain a system of equations. However, in this problem, we are not that sure about the orientation of this rigid bar. I'm not sure whether the rigid bar is inclined like this or like this. It is not that intuitive, so we have to do some reasoning on it. To do this, we consider the change of length formula for S1 and A. For S1, still we use the L pi equation. We put the values inside, we take the common factor out, and we compare their denominators. Besides, from equation 3, we have PS1 is greater than PA. So compare those two, we will observe that PS1 is greater than PA. Also, the denominator of PS1 is smaller than that of PA. That means the change of length of S1 is greater than that of aluminum wire. That is, delta S1 is greater than delta A. After that, we can confirm that this bar is rotating in this way. Then we have to take the maximum allowable elongation to that of the steels, because as usual, the steel wire on the left hand side is the one with the largest elongation, because as steel wire on the left hand side has the largest elongation. As found in part A, the allowable load in the steel wire is 691 newtons. By geometry, we can write this form, that is, the change of length of S2 is the average of that of S1 and A. Rather similarly, we apply the change of length compatibility and put our change of length formula into this compatibility equation. We simplify this equation and substitute the values into it. We do a lot of calculation and simplifications to get the expression of PS2 in terms of PS1 and PA, while PS1 is a known quantity because it is said to be 691 newtons. Actually, at this moment, we have 3 equations to do. Recall that our ultimate goal is to find allowable load P. Therefore, for those 3 systems, we solve for P. Do a lot of substitutions and calculations. You will eventually get P equals to 703 newtons. Those things will leave to you as reading. You should read through those steps to understand why you have such answer. You should also mentally prepare for those kind of problems in the exams. It is not easy, and sometimes you need a lot of time to do the computation.